screen. Oh, it works perfectly. Very fine. Okay. The title is Verification of the Incremental Merkle Tree Algorithm with Dafny. Franck, the floor is yours.
Thank you, Dorel. So I hope you can hear me well.
Yeah, very well.
Perfect. So I'm Franck. I'm at Consensus in the Trustworthy Smart Contracts verification team. And I'm going to talk about the formal verification of an algorithm, the Merkle tree algorithm. And the formal verification was carried out with a verification-friendly language called Dafny. So, first, sorry. So why is it important to verify this algorithm? It turns out that this algorithm is used in what's called a smart contract, which are the programs that run on the Ethereum virtual machine. And usually these programs, they manage a lot of assets. And the second thing is that once you deploy these contracts, they are somehow immutable and just stored in the Ethereum blockchain, so you can't modify them very easily. So if there is a bug in them, it may be hard to modify them and to fix the bug. And as they manage a lot of assets as well, if there is a bug, they can be exploited to steal some assets from let's say, the assets that are in a contract. So just to give you an idea of, let's say, how a smart contract may look like, and this is an excerpt of the code of a deposit smart contract, which uses the incremental Merkle tree algorithm. So you see that in this code, you can write the code in a high-level language called Solidity, and you don't really need to understand the code, but just to give you an idea that the contract that's been deployed may contain some errors. It's been tested and analyzed, but you see that there's a comment from the developers stating that hopefully we should not get at this program point. And to make sure to be safe, so that's what's asserted, to be safe, we assert false. So actually in the Ethereum virtual machine, if you were to reach this program point and the assert statement would be failing, you would what's called revert the transaction. So revert the effect of this function call to the state the system was before. So that's true that, let's say, adding this assert statement make the code safe. But in reality, you would like to check that this can never happen. If it's supposed to not happen, you would like to formally check, for instance, that indeed this assert statement is never going to be reached. And also, you'd like to check some other properties like functional correctness. So in the next few slides, I'm going to try to explain what the Merkle tree, how Merkle trees are used, what the incremental Merkle tree problem is, and what we did to verify the algorithm, incremental Merkle tree, that's implemented in the deposit smart contract, which carries a lot of assets again, and it's important to verify it. So, all right, so Merkle trees are used to provide a compact encoding of collections of elements. So I'll give an example here, which is you have a list. And for instance, over the Ethereum network, you would like to compare that two lists are equal or different. And you don't want to communicate to the different participants in the network the full list. So what you can do is to use a compact representation in the form of a tree. And the tree is just meant to be able to compute what's called a number, a root hash. And the way it's computed is as a synthesized attributes. So we'll take this list and we'll build a binary tree with enough nodes. So in my case, I need at least 8 nodes. So the tree is a binary tree, and it's also perfect or complete. So it's got all levels filled with nodes. And then we put the list at the leaves from left to right. And if the actual initial list that you have has less than the number of leaves of your tree, you pad it, you right pad it with default values. So in this case, it's 0. And then we synthesize a number. I'm going to use, in this case, a simple function combining two children of a node, which is left node minus right node minus 1. So we synthesize a value at the root, and it's called the root hash. And in the actual Merkle trees in the Ethereum network, we don't use a simple function like the hash that I have on the left-hand side, but we use real hash functions. So it's very unlikely that when you compute the root hash for two different lists, you would have a collision, so you would have the same number. So it turns out that computing the hash root for a given list using a Merkle tree will give you actually the ability to check whether two lists are equal or not. You just have to compare the root hash, and it's again the probability that the root hashes are equal and the lists are different is very low. So there are other things that you can do with Merkle trees, but in this talk I will focus on computing the root hash, which is let's say the main function that is implemented in the smart contract, the deposit smart contract that uses these Merkle trees. So now, what is the incremental Merkle tree problem? So it turns out that if you have lists, and that's what's happening in the deposit smart contract, you may append elements to a list. And in this case, so that's what's happening in my list. For instance, if I append an element 5 in the 6th position, you'll see that to compute the new root hash, I'll have to work again to modify the computation on the nodes of the tree to compute the new root hash. So it turns out that you can see in this example that actually the subtrees on the left-hand side and right-hand side of the path leading to the leaf where I inserted a new value are not modified when we compute the new root hash. So the incremental Merkle tree problem is the following. We're going to have, let's say, a list of elements that can grow monotonically. So you can see at the top here, at the beginning, I insert a value, and then I insert a blue value, an orange value, and so on, and you never remove a value from your list. So you would like to be able to encode and compute a compact representation of a list, the root hash, in an efficient manner, and you're given the ability to store lists, I would say, of 2 to the power of h+1 elements at most. So you have a tree of fixed size, h. And the incremental Merkle tree problem is the following. Can we find an algorithm which can compute the root hash for the successive, let's say, Merkle trees that we obtain by appending elements to a list, one by one? Can we find an efficient algorithm? And in this talk and the work we've been doing in this project is, if there is an algorithm, can we prove that the algorithm is correct? So the answer to this question is we can find an algorithm. An algorithm was proposed by Vitalik Buterin a few years ago in what's called the progressive Merkle trees. So the algorithm exists. And in this work, we're going to prove that it's correct. So you can see that the description of the computation that I provided before, if you want to compute the root hash, you have to walk through all the nodes. So again, it would be an exponentially expensive computation, and you want to show that there is a more efficient algorithm to do so. Otherwise, it would be impractical. So just a hint about how to design the algorithm. So you can see that if you want to compute the root hash of a given tree, and let's say we insert a new value at a given index in the leaves of the tree, we don't actually need to remember all the values of the nodes that we computed before, but we just need, on the given green path, we just need the values of the siblings of the nodes that are on this path. So this somehow suggests that if we can use a compact representation of a given Merkle tree that we have obtained up to a given point after inserting a number of values, this suggests that if we can represent the state of the current tree with the values of the left sibling of the current path and the values of the right sibling of the current path, we may have a compact encoding of the tree, and this may be used to actually incrementally compute the root hash. So this is, if you remember your crash course on algorithm design, theory and design, this is similar, and this is exactly the case. This is dynamic programming to compactly encode the state of a problem and to reuse computations that you've done before. So that's what's happening in the incremental Merkle tree algorithm. The state of the system, so the current root hash and the state of the current tree is maintained by two arrays, left and right. And these arrays are updated when you insert a new value at a new leaf. Right, so what did we do to formally verify the incremental Merkle tree algorithm? So first, I have to explain that to you. The algorithm inserting a leaf in the tree and computing the root of the tree, these two algorithms are separating the smart contract that implements the computation of the root hash. So why is it so? So you could imagine that you have one algorithm inserting a new value at the end of the list and computing the root hash. So in the Ethereum virtual machine, this would cost you some, let's say, insertion costs. You'll have to modify the state represented by the two arrays, left and right, and another state variable that would be the root hash. It turns out that in the Ethereum virtual machine, computation have a cost, and it costs more when you modify the state of your contract, let's say, of your object, rather than when you don't modify the state. So that's why the algorithms that were proposed a few years ago were split into two. There's one algorithm that modifies the state of a contract, of the variables, and one algorithm that reads the state and compute the root hash. So it's less expensive in terms of cost in terms of gas, which is the currency used to measure how much computation costs on the Ethereum virtual machine. It's less expensive to split the two computations into two, and it's less expensive not to store the current root hash, but to ask every node to recompute it because it doesn't cost anything. So that's why it's split into two. So these are the two functions that are implemented in the smart contracts, the deposit smart contracts that uses the efficient Merkle tree. So the two arrays that I mentioned before, they are in the actual algorithms called the branch for the left array and zero hashes for the right array. So you see that the algorithms are fairly simple. So actually, these ones are the algorithms I derived in this project. The original deposit algorithm is different to this one. This one is an optimized version of it. So what do we prove? What's the main invariant that we're going to prove? So we have at the moment, let's say, you've inserted a certain number of leaves, and the current path to the current leaf is the purple one. And we represent, let's say, the state of the tree. Of course, we don't want to build this tree, but we represent the state of this tree by a counter C1, which is the number of values that we have inserted so far. The left and right arrays that I mentioned before, that contains the values of the siblings on the purple path, for instance, on the left and on the right. And the function deposit, which will add a new value at the end of the list, will modify the state. So we'll increment the number of values that we have stored by 1. We'll modify the left vector representing the values of the siblings on the left of this orange path. And it turns out that we can prove in our formal verification work that the values on the right-hand side, the array that we use to store the values on the right-hand side, is constant. So we don't need to modify it. And the main property that we want to be maintained, the main invariant that we want to be maintained, is that when you compute the root value using this state on the first tree, if you insert a new value, you get a new representation, a new state. And if you recompute the root value, you would get the root value that you would have had if you would have used a Merkle tree, right? So we want to get the same values at each point in time without building the trees, but with using the state variables that provide a compact representation of the tree. So that's what we have proved in our work. So what are the other things that we have proved? So these are the same two algorithms that I mentioned before. So you can see that they are array accesses. So you would like to prove that it's impossible to have a runtime error, which is an array out of bounds. So can we prove that every time we access an index in the arrays, it's a valid access to a value? There are also arithmetic computations in the methods of the contract. So You'd like to prove as well that there's no overflows or underflows. There are loops in the contract as well, so we would like also to prove that the loops terminate. And there's two arrays, for instance, used in the contract. So you can think of a contract as an object. So you would like to show that there's no unwanted aliasing, so memory safety, that you're not modifying by mistake a value in your system. So right, so this is the code look like, the verification, the annotated code look like. We use the verification friendly language Dafny. So this is Dafny code. And in Dafny, you reason with OR triples using Floyd logics. So it's hidden because there's a solver providing the reasoning for you or checking your reasoning. But you write, you can write assertions, annotate your code with assertions. You can, so this one, for instance, can check that there's no overflows. You can write loop invariants and also ranking functions to prove that the loop terminate. And of course, we have proved the functional correctness of the algorithm. So you see that this one, it's a post condition. So preconditions in Dafny are written with requires and post conditions are written with ensures. So in the code that I just mentioned now, the valid predicate captures memory safety requirements. And the other ensures at line 4 captures the fact that the result R that is computed by this function is the same as the one that we would have obtained if we had used a Merkle tree. So these values variable contains all the values that have been inserted so far, and it's called a ghost variable in Dafny. So it's a variable that's not needed to run the program, but that's needed for the proofs. Right, so what are the results? So we have provided the repository with the full code of deposit smart contract in Dafny. So we check the high-level code, the Solidity code, and written as Dafny code. There is in this repository a Docker container if you want to run the proofs. So when you write the program and you use Dafny, Dafny can check the proofs and the invariants for you. So when you're done and you have found the correct invariants and the pre and post conditions, you've got a machine checkable proof that this code is correct. So we have proved the absence of runtime errors. There's no array out of bounds. There's no underflow or overflows. To do that, we use the invariants. Termination is proved by using ranking function. Memory safety, so no aliasing or no unwanted aliasing is proved using dynamic framing invariants. You can write them in Dafny as well. And functional correctness, which is the main property that we have proved, which is, again, this compact encoding with two arrays of the state of the current tree can provide exactly the same result as if you had built the Merkle tree. And we've got some invariants that are, of course, valid all along the life of the system. You can think about that as something that's always true after any amount of values that you've inserted in your list to represent as a Merkle tree. So what have we done? So for instance, for the code I showed at the beginning, we also proved actually that this statement cert false is never reached. And you can see actually that this implies that the loop will never actually, the height variable, which is the index of the loop incremented at every iteration of the loop, will never reach the top value of this constant value, because otherwise it would exit the loop normally. So we can prove that. And what we did was actually to come up with a simpler version of this deposit version without, so I could compare the two. This one is a for loop with an if statement embedded in it. Turns out that the for loop always returns early and that never exits at the end. So what we have provided is a simpler version of it, of this algorithm that doesn't have to check with an if statement whether something is true or false, but relies only on a single while loop. So it's more efficient gas-wise, I would say. So when you pay for it, you pay a bit less. So in terms of statistics, we used the verification-friendly language Dafny because we had some previous training with Dafny. So we could have used Y3, Viper, Wiley, and probably other languages to perform the same tasks. The verification effort was around 12 person week. This included actually the design of the proof for the smart contract. There were around 100 theorems proved, so they range from simple ones to more complex ones when it comes to proving the main functional correctness property that we compute the same thing as a Merkle tree. Overall, there's around 3,500 lines of code. So these lines of code include the actual implementation that I showed before, plus some functional equivalent or somehow functional let's say, equivalent of the computations that we use to prove functional correctness. The code is also documented, and at the end of the day, we have proved that there were no runtime errors and that the algorithm was computed as expected. So there's a short breakdown in terms of how the repository is structured and some more detailed statistics that you can read in the paper. So overall, the code of this, the scope of the work was to design a machine checkable proof of a deposit smart contract. So we've proved functional correctness, absence of runtime errors, and termination. The main findings is that it's doable to do it in a reasonable amount of time. A language like Dafny is also mature enough to support this kind of work. The main things that we have found is that there are two optimizations that you can have. As I mentioned before, you can optimize the deposit function with the code that I showed before. And there's also another one, which is initializing the values of one array that you don't need to initialize. Actually, so you don't need to set the values to the default values of 0. So overall, we provided some code. There are links as well that you can access. There's a GitHub repository with the code, with a Docker container to run the proofs yourself. We wrote a paper, this paper at Formal Methods, and there's a long version of it on the archive. And there's also a short blog explaining how things work. So just to conclude, there were some previous work on the formal analysis of a deposit smart contract by people from runtime verification. It turns out that they provided some bits of proofs, I would say, for the verification of the smart contracts, but there was no continuous proof that I would say, or complete proof that the algorithm was functionally correct. Different to our work, they also proved when they talk about an end-to-end formal verification, they also proved some correctness about the bytecode that's generated from the Solidity code, the bytecode that runs on the Ethereum virtual machine. But the bytecode is proved using a manually written functional specification and not a specification that's derived from a top level one written in a formal language. So that's it from me. And if you have questions.
Okay. Thank you very much, Franck. Very nice presentation, very nice work. Okay, we have time, a very short time for one question or two.
I have raised my hand. Can I ask you?
Oh, yeah, please go ahead. Work
Okay.
on, please.
Yes, thank you. So thank you for a very interesting and nice talk, very interesting work. However, there's something I did not understand. Maybe you can help me there.
Mm-hmm.
So one thing is that you already in the motivation slide, you talk about a particular smart contract as an example, and you talk also further down in the talk about verifying a deposit contract.
Mm-hmm.
And that is the application layer, right?
Mm-hmm.
So we have, and that is one problem to solve. How do we do good verification of smart contracts, which are the application layer of Ethereum? Yeah. But also the talk is about verifying Merkle trees and algorithms of Merkle trees, which is then in the EVM. That's somehow the hardware in some sense, right? It's the computational model which underlies the application layer. But somehow these things are kind of done together, or how do they relate? In particular, you have slide number 14, where these things seem to be kind of mixed. You understand my question? I do not.
So the first thing I would say is in our work, we didn't verify the bytecode, right?
Yeah.
So we verified the Solidity code, which is an imperative language similar to the Dafny language, right? So then, if I understand your question, so the functional correctness verification is hidden somehow inside line 4. So this build Merkle function is written as a function in Dafny, and it says, so we have a library in our work which implements Merkle trees, right? So,
yeah, so maybe I can interrupt you here. My question is all about the following. Merkle trees are, and the algorithm which work with Merkle trees are part of the EVM, not of the smart contract, right?
No, they're not part of the EVM.
No?
No, there's no, I mean, the actual work that we've done, you see that the code that runs in the smart contract, it doesn't have any Merkle trees. It's got two arrays representing Merkle trees. So Merkle trees in our work, they are written, there's some code in our Dafny project. There's some code for creating Merkle trees and manipulating Merkle trees and so on, which is a sort of a reference specification, but it's not executable. We could execute it, but we don't. And this build Merkle function, you take the root of this, it simulates the computation of the root hash of a Merkle tree, and it's written in Dafny, but it's not used in the actual smart contracts.
Exactly. That's my point. You do the smart contract verification at the same time as you do this verification.
Yes, we have to have, this is the reference, this is the functional correctness. It's equivalent, if you wish, as if you had an algorithm that would sort a list, you would like to write at the end, the list is sorted. So we write here at the end, the result is the same as the one we would obtain if we had built a Merkle tree.
Okay.
Does that answer the question?
Yeah, maybe, but we can maybe take it offline.
Yeah, be happy to chat here. Yeah. Thank you for your question.
Okay, thank you. We have a question in the chat from Malte Sberhoff. Thank you for clear talk. And can you say a bit more on the ratio of executable code versus Dafny proof annotation?
Yeah, I can talk about that. So I think it's around 90% of the code is proof. You see that the algorithms are very simple. So there are lots of proofs related to and annotations actually. So annotations, it's a bit less than proofs, of course, because an annotation is what you see on this slide. But sometimes in Dafny, you have to help the Dafny verifier, providing some hints how to prove invariants. Or so this code, for instance, the get deposit root on this slide, in the actual version of it on the repository, there's much more code with the proofs. So it's not only annotating the code with the specification, I would say, but with hints how the verifier can verify the proofs. So the ratio is almost 90% of annotations and proof code. So you write the proofs as programs in Dafny against 10% of actual code.
Okay, thank you. And another question from Alan Lee. Thank you for the talk. Is the code translation from Solidity to Dafny automated?
No. So the code translation is not automated. So for this simple project, it's quite easy to translate manually. So for, let's say, a single verification work, it's okay. If you want to translate the code, the Solidity code to Dafny, that's actually something we're doing at the moment, or we're investigating. It's not very easy because the two languages, they don't have the same features. So Solidity has some specific features, for instance, to deal with data structures like mappings, or to deal with hierarchical, let's say, programs using classes and inheritance and so on. These features, we don't have the equivalent in Dafny. And I think there's no equivalent either in other verification-friendly language like Y3 or Wiley or Viper. So it's hard to map Solidity, to write let's say, a compiler from Solidity to Dafny. And it's also hard to write a compiler from Dafny to Solidity.
In that case, how difficult it is to translate the verification from Dafny to Solidity?
Also, in this particular case, we have assumed sort of a shallow embedding. So we have assumed that the semantics of while loops and some, let's say, data types like integers and so on is the same in Solidity and Dafny. So the code is sort of a one-to-one mapping from Dafny to Solidity. So it's a shallow embedding.
Shallow. Okay, thank you. Any questions? No. Thank you very much again. We are a bit late.